In this discussion, I'd like to talk about the representation of two of our data types. I'd like to talk about integers and also about real. For an integer, the statement integer : I sets aside 32 bits of memory with the label I associated with it. The 32 bits you can think of as indexing 1 through 32. So an integer is D1, D2, D3 out to D32, where each of the DI numbers is either 0 or 1, depending on which integer value that you're looking at. Because an integer has only 32 bits, and because each bit can only be 0 or 1, there's actually a finite number of the integer data value types that Fortran can have. In particular, that means that there's a biggest integer. Now, because you have positive and negative integers, you need some way of indicating that. So 1 bit out of the 32 is assigned to indicate whether the integer is positive or negative. That leaves you with 31 bits. So in the kind of setup that we're looking at, the largest integer is a string of 31 ones in base 2. I'm going to make up a letter to call the largest positive integer. I'll call it Z. This string of ones, this is 1 times 2 to the 0 power, plus 1 times 2 to the first power, plus 1 times 2 to the second power. This will continue until you get to 1 times 2 to the 30th power, not 31, because we started off with 0 for a power. So Z is going to be 2 to the 30 plus 2 to the 29, all the way down to 2 squared plus 2 plus 1. To figure out what that number is, we'll use a trick that's very similar to things you did in Calculus 2 when you were talking about geometric series. I'm going to figure out what 2 times Z is. So I'll just take all of these terms and multiply them by 2, which has the effect of increasing the power of 2 on each one. So you'll have 2Z is 2 to the 31 power, plus 2 to the 30 power, which you notice is in Z, 2 to the 29, 2 to the 28, all the way down to 2, which is also in Z. You see that there are many terms in common. So if you take 2Z and subtract Z from it, the only things that don't cancel out are the 2 to the 31 from the 2Z. The 2's cancel out, and you have minus 1. But 2Z minus Z is just Z. I figured out on my calculator what 2 raised to the 31 power minus 1 is, and it works out in decimal to be 214748367. If this reasoning is correct, this is the biggest integer that I can have in terms of a 32-bit integer, that is. So I've written this Fortran program, and what it's going to do is it's going to set integer I equal to this allegedly biggest integer value and then print it out. And then we're going to go deliberately looking for trouble. I'm going to increase I by 1 and then print out the result and then do it again. After we do that, I'm going to set both I and j equal to this alleged biggest integer value. I'm going to add them together, which should certainly cause some sort of trouble, store that into variable k, and then print the k out. So if we run that in the usual way, the good news, the alleged biggest integer, is correctly printed out. When I add 1 to that, it rolls over and becomes negative and large, which may not be a terrible shock because we had that 1 bit set aside to indicate whether the integer was positive and negative. And probably what's happened here is by taking the biggest positive integer and adding 1 to it, I've caused the sign bit to get flipped. After that, though, it gives me a bizarre answer, but it is correct. If you take the number that the cursor is beside right here and add 1 to it, that is the correct result. So in a certain sense, it's doing as well as it can. If I take the largest positive integer and add it to itself, though, I get -2 for an answer. We need to be aware of the possibility of this kind of behavior, which we're going to call integer overflow. Even at this early stage of the game, we can see two things. It's a bad idea to add two integers if they're very large, because this overflow wraparound thing is liable to happen to you. And for the same reason, it's a bad idea to multiply two large integers. If we wanted to write a program to calculate factorials, for instance, this is an indicator that doing it the naive way by multiplying a bunch of integers together is not the way to go. We'll have to figure something else out. I was going to make some comments about compiler flags, but I'm going to put that off for a while. The situation for real values is similar, but the structure is totally different. Again, for a real, we're going to set aside 32 bits. The decimal point, I really should call it a binary point, is not really stored. We need to have some way of determining whether our number is positive or negative. So conceptually, we set aside 1 bit from that. We're going to set aside 8 bits for this exponent. We will represent our numbers as a binary point, 24 binary digits times 2 raised to a power, where again, we've set aside 8 bits for the power. Now, if you take 8 bits away from 32, that leaves 24. If I use 1 bit for the sign of the number, that would make you think that there's only 23 bits left. By a clever trick, we will get our extra bit back again, though. Each one of these bits is either 0 or 1. We can always make changes in the number, shifting the digits one way or the other and changing the value of j to make this first one, d1, equal to 1. This is called normalizing the number. If you do that, you suddenly realize you don't actually have to store d1 because it's always going to be 1, which means d1 has become an abstract thing, which is always 1. And then you use these 23 digits that you've got, and magically you've got 24 binary digits back again. It's a very clever trick. But what about the j? We're representing our number as plus or minus point d1 through d24 times 2 to the j, and we only have 8 bits to represent j. The power on the 2 could be positive or it could be negative, so we need to set aside 1 bit for that. Unfortunately, there's no trick like it was for the normalized mantissa to get our bit back again. So this really only leaves 7 bits for the rest of the power. I want to think about the biggest possible power the biggest possible j in the 2 to the j. So 1, 2, 3, 4, 5, 6, 7 ones. This is some integer in base 2. 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2, and continue until you run out of ones here. Get the calculator out and check it. That's equal to 127 in base 10. So the biggest real is going to be 24 binary bits after a decimal point. I suppose it really ought to be called a binary point. In any case, times 2 raised to the 127 power. If you do the same kind of geometric series type approximation as before, you'll find out that if you write down the binary point and then 24 ones, this number is very nearly equal to 1. So I'm going to say that the biggest real is, roughly speaking, 1 multiplied by 2 raised to the 127th power, which, if you calculate this using a calculator, comes up to be about 1.7 times 10 to the 38th power. This, roughly speaking, is the largest 32-bit real value that we can have. In this program, we're going to investigate the issue of the biggest real, because once again, we have only a finite number of bits, both in the mantissa and in the exponent, so there must be a largest one out of all of these. Initially, I set x equal to 1.0. I say 1.0 instead of 1 is kind of a mental reminder to myself that we're talking about floating point numbers. I'm going to go around in a loop a number of times. Each time I'm going to double x and then print it out. So the first thing that I should see printed should be 2 times 1, which is 2. I go around and do this 130 times. That's the end of my program. I tinkered around with the upper limit on the loop until I could see where the numbers were getting close to 10 to the 38th power. I've already compiled this. So when you run this, if I just run it as is, the numbers are going to stream off the screen so quickly I won't be able to read anything. So I'm going to pipe this through less. As you can see, the first number that's on the screen is a 2, just like we said it was going to be. Then 4, 8, 16, 32, 128, 256, and so on. The numbers are doing what they're supposed to do. They're doubling on each iteration of the loop. By the time you get to the end of the second screen, your numbers are in the range 7 times 10 to the 13th power. The e plus 13 means scientific notation. Now we're up to 5 times 10 to the 20, 4 times 10 to the 27, 4.1 times 10 to the 34. We're getting very close to where we think the largest real can be. And in fact, I actually see a 1.7 times 10 to the 38th power on my list. And when I try to double that, the computer presents me with this character string infinity. So just as with integer overflow, you've got to be careful that you don't get real numbers that are too big, or something similar will happen to you. I'm going to leave what happens in double precision as one of our first homework problems. If you had some exact decimal number which was converted into binary, The binary digits of that number most likely will form an unending string of digits. But when we try to store that into our computer, we have a problem. I have only 24 binary digits to work with, so some sort of rounding or chopping is going to have to be done to the rest of it. This is going to have consequences for us. So in a typical situation, if I've got some number and the floating point version of it, by floating point, I mean in this case, 32-bit floating point. Typically, the difference between the exact and stored number is you'll have a bunch of zeros, and then you'll have a 1, probably in the 25th slot, although if you get lucky, further out, times 2 raised to some power j. The absolute error is the absolute value of this difference, which, as we've seen before, is going to be roughly 2 to the negative 25 times 2 to the j. Now, because of that 2 to the j, this absolute error here could be really big or it could be really small, but that's hard to tell the meaning of. If I told you that this difference was 10 and then asked you, is that a lot or is it very small? It'd be difficult to say because you don't know the scale of the thing we're talking about. If the absolute error were 10, but the true exact number was 40 billion, then that would be excellent. If the absolute error was 10 and the actual value of the quantity you're interested in was 2, that would be horrific. So what we do very often is we take the absolute error and divide it by the exact value. This has the effect of getting rid of the scaling factor. It gets rid of the 2 to the j. So in a 32-bit real, if you take an exact college algebra type real number and slap it into the computer, typically what's going to happen is the relative error is going to be roughly this size. The 2 to the j's cancel out. The number on the bottom, if all of the di's were 1, this number would very nearly equal 1. If only the first one was 1 and the rest of them were 0, this number would be 1/2. The number inside the parentheses is between 1/2 and 1. So it's not very big, it's not very small, it's not terribly different from 1, really. So typically, the relative error in this procedure is going to be about 2 to the negative 25 power, which if you get on the calculator is 3 times 10 to the minus 8. When we say that we expect relative errors to be about 10 to the minus 8, that means we expect to get about 8 decimal digits of accuracy. And by decimal digits, I mean in the mantissa, not thinking about the exponent or anything. This also gives us a measure of how good our calculation methods are as well. If I was doing some big complicated calculation using 32-bit reals, and at the end I had an answer whose relative difference from the true answer was less than about 10 to the minus 8, I'd regard that as complete success, because if somebody had just handed me the answer and I put it in the computer, that's how much error would have been committed anyway. There's another effect that we need to be aware of, and the only reason it happens is because of the way we're storing the information in the computer. Suppose that x was 1.2 times 10 to the 7 power, which is well within the set of numbers that a 32-bit real can have. Y equals 3.5 times 10 to the minus 6. We haven't talked about the smallest positive real, but it turns out that that's well within the acceptable range as well. Set z equal to x plus y and print z out. Z should be bigger than x, strictly bigger than x, but there's a problem. I'm going to emulate the 32-bit behavior by using decimal arithmetic with 8 decimal places. So if I write x in sort of the kind of format we were talking about before, it'll be 0.12 and then 6 zeros times 10 to the 8th power. Y is going to be 0.35 and a bunch of zeros times 10 to the negative 5 power. What I can't do is I can't just take 1, 2 and add it to 3, 5 because the powers are different. So what I could do is I could take all these digits and shift them to the right and put a 0 in, which makes this number 10 times smaller than it used to be, and then increase the exponent on the 5, which will make that number 10 times bigger than it used to be, and then just keep shifting and adjusting the exponent until this negative 5 has been made into an 8. So I've done my counting off scene. There's my x, y, the number of smaller absolute value. After you get done shifting it enough so that the power on the 10 is 8, this is what you get. The two exponents are now the same, so I can take this mantissa and add it to this mantissa times 10 to the 8th power. Now, if this had rolled over and had become 2.5 something times 10 to the 8, I would have had to shift the 2 to the right and adjusted the exponent again to make it one of these normalized numbers. Luckily, that didn't happen. The thing about this is, when I store this out to memory, I've only got enough storage for 8 decimal digits. 1, 2, 3, 4, 5, 6, 7, 8. Everything after this vertical line is in trouble. The 3 is not as big as 5, so you chop it off and you do not round this. You get 0.12 times 10 to the 8th power, but that's x. I've taken two positive numbers, x and y. I've let z be x plus y, and the thing that's actually going to get stored out to memory is x, which shouldn't happen. It's as though adding the y doesn't do anything. I'm going to call this the big number plus small number effect. So we'll have this program. I've got real x, y, and z. I'm going to make x real big and y not so big. X is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9.0. That's a pretty good sized number, but it's not anywhere remotely close to the biggest possible real. So don't think that that's the problem. Y is going to be 1.2. I'm going to print out x, y, and z, which is x plus y. Then I'm going to print out the difference, z minus x. If we were doing exact arithmetic, since z is x plus y, then z minus x would have to be y. That difference that I'm printing out at the end in exact arithmetic would come up to be 1.2. So I'll go ahead and compile this and then run it. There's x, y, and z, and when I calculate the difference, z minus x, which is supposed to be 1.2, I get 0, which is obviously wrong. This is due completely to the big number plus small number effect. There's something else though too. Where did this 1.2 whole bunch of zeros and a 5 come from? So we need to talk about that as well. It's easiest to illustrate what's going on with 1/3. So real variables, x is going to be 1.0, y is going to be 3.0, and z is going to be x over y, which would be 1/3. Now this is the floating point 1/3. So when I print out x, y, z, I expect to see 1 and 3 and 1/3. So I've already compiled it. Let's run the thing. So I get my 1, I get my 3. If you think about it, 1/3 is an infinite repeating decimal, and all of the digits are 3. If you're going to round that for some reason, you would never ever round up. And yet here we see several 3s, and then a 4, and then a 3. If we were doing exact arithmetic, that could not happen. So what's going on here? In binary, if you write out what 1/3 is, it's a infinite repeating binary type number, just as it is in decimal. But unlike what happens in decimal, the digits aren't all the same. 1/3 in binary is 0.01010101, and so on and so forth. We only have so many bits to store. So what if you're going to have to round this, and the last digit that you know for sure that you're going to include is that one? The next one would be 0, and then there would be 1010, and so on. This would not cause that to round up, so it's just going to chop it off. The number that you're going to get is what you would get for the exact value of 1/3, except you're leaving off some positive contributions. If this happens to you, the number that you're going to get will be less than 1/3, guaranteed. On the other hand, what if the last digit that you're going to include for sure is that one? For rounding purposes, you look at this. In binary, you only have 2 digits, 0 and 1. 1 is more than half of the biggest digit, more than or equal to. So this is going to round that 0 up to 1, and you'll get this for an answer. Depending on the details, that may actually give you a number bigger than 1/3. For the example we were looking at, in this first case, you get 0.33203,125, which is smaller than 1/3, which is what you expect because you have failed to include some positive contributions from all of these latter digits. The other one, when it rounds up to 1, you get 0.33398375. This is bigger than 1/3. So if you see some odd behavior like that 5 done at the end of the 1.2 or the 4 in this 1/3 program, it's completely due to the way we're storing the numbers and doing the arithmetic. There's one last specific issue that I want to talk about. Suppose that you were calculating some things. You've done a lot of calculating, 32 bits, 8 decimal accurate. You ended up with these two numbers, x and y. X is this number, y is this number, and the underlined digits are the digits that are not right, which could be caused by storing numbers into memory or previous rounding errors. If you look at x by itself, only 2 digits out of the collection are not right. So whatever quantity this x is supposed to represent, this is a very accurate representation for it. And the same is true for y. Then the bad news, at some step in your calculation, you have to take these two extremely accurate numbers, x and y, and subtract them. When you do that, you get this for a result. Now, we're going to do the normalized thing. I want to rig it so that the first digit after the decimal point is not 0. So I'll have to multiply this by 10 4 times, and I'll get 0.167. When I make this bigger by a factor of 10 to the 4, I've got to make this smaller by a factor of 10 to the 4. So we'll lower the power on the 10 4 times. That detail is not important. What is important is there's only 3 digits in my answer. The reason that the 6 and the 7 are underlined is they came from the wrong digits up here. In all likelihood, the 6 and the 7 are wrong. That means in this calculation, I've taken 2 extremely accurate numbers, done a terrible thing, and in the result, I have exactly 1 digit of accuracy left in the z. This is called catastrophic cancellation, and this is something we'll definitely have to worry about. So we now know some things that'll be of concern to us from time to time. In the videos, we saw that division of integer by integer doesn't quite act the way you might think it would. Also, you need to be careful about integer overflow, also real overflow. Never add or subtract 2 floating point numbers that are of hugely different magnitudes, because you'll get the big number plus small number effect. And never subtract 2 numbers that are nearly equal, because you'll lose much accuracy by doing that. This seems to put us between a rock and a hard place here. As we go along in our algorithms, sometimes these issues will rear their heads and we'll have to deal with them. One last thing that I wanted to talk about has to do with the options in a compiler. A compiler is a hugely complicated set of programs designed to take your source code and turn it into something that the computer can actually execute. Without fail, for a given compiler, there are ways to set different options, set different default values, set different presentation values, change how the code is generated, change, in fact, all kinds of things, all of which can have an effect on your answer. To give you a clue as to how big a set of options we're talking about here, I'm going to look at the manual page for Fortran over on the Linux side. This is just to show you how complicated this actually is. This is the command you issue to see all of the options for the Fortran compiler. As you can see, it looks like there's a lot of stuff. And then you go on and you find out that there's a lot more stuff. And then more stuff after that. You can issue various error and warning options. Then there's runtime options and link options, code generation options. Then there's a whole bunch of other options. Then after that, there are some options. and then some more options, followed by some options, and finally you get down to the end of the manual page. There is an almost unbelievably large number of things that you could set and specify, all of which may have an effect on some of the digits in your floating point calculations. We'll look at this a little bit as we go along, but obviously we can't look at much of it because it would burn up our entire semester. In our next discussion, we're going to start looking at numerical methods to solve the equation f of x equals 0, where x is an ordinary number. This may seem like an extremely silly thing to start with, but as we're going to see, it's not at all. By the end of the semester, being able to do this will be of vital importance to what we're doing. I hope everyone has a good day. I'll see you in the next one.